All right, so we got about 20 minutes before the class starts. I just click on the streaming, so YouTube should get the content right about now. Okay, very good. And let me check one last message. Okay, all right, cool. All right, so I got some questions about the lab that was due today. Some people asked me over the weekend or yesterday, and then some people wanted me to share the answer or basically the technique of how to answer those questions today. So those are all good. So let's go ahead and get started with that first. All right. Oh yeah, problem 4 is one of the more interesting ones. And this is what we are at. Nope. Moving on, move. Floating point 2. Okay, that's the lab. All right. So we'll go to preview mode. So that means, I'm getting a set of problems just like you guys do. All right, so we'll look at question number 1. So question number 1 is asking if I need to find a p, an integer p here to maximize the left-hand side, but still make it so that it is less than or equal to the, I have to choose an integer p to maximize the left-hand side, but I still want it to be less than or equal to the right-hand side. So the question is, how do we do that when x equals to 2,543,987? So there are several ways to do this. The first one is, and I don't really care which way you do it, okay? Because the whole idea is to get an idea of what is 2 to the power of p doing, because that's basically the magnitude. So let's go ahead and do this. This one, by the way, is related to maximizing a value before we divide it by 10. Because last time that was eons ago, because we talked about this last Tuesday, that in a division, we want to maximize the dividend or the number being divided, otherwise known as the numerator. And because we are also dealing with 64-bit numbers, so we can't make it too big. We can only make it big enough that we can contain it in 2 to the power of 64 minus 1. All right. So this one is not too bad, okay? Because let me show you one way to do this, which is, I think it's just as legitimate as any other way. But some people may look at this and go like, that doesn't look very, efficient. But efficiency is not really the big deal here, because what we want to do is to get a sense of how these values work. So I'm just using a spreadsheet, and I will express x over here, and it's 2543987. Okay, so we want to find a p, and we also want to define the boundary. So the boundary in this case, let me put the spreadsheet back here, is 2 to the power of 64 minus 1. Oh, the minus 1 is outside of the parentheses. So it's a pretty huge number, okay? But this, by comparison, even though it's 2 million something, it's really small compared to this one here. So now we want to look at the value of p, and you don't have to guess it. You can basically just start with something like, okay, let's start with 2 to the power of 0, okay, which is 1. And then you look at whether this number times this number is still less than or equal to this number over here. There's a plus 5 somewhere. Okay, let me fix this. There's a plus 5, which really doesn't change things too much, and the answer is true. So now I have to go back here and modify a few things, because when I refer to B1, I don't want, by copying and pasting this formula to another cell, if I don't do a $, it's going to quote unquote float with it. So I need to make sure that the row number is not floating for B1. And the same thing applies to C1, because that's, I want every single row to refer to B1 and C1 and not to change. The A3 is okay because I want every equation of every formula to refer to the value that is to its left-hand side. All right, so there we go. And now we look at the second row. And the easiest way to do this is to say this row, the value of this cell is 2 times the value of the cell that is right on top of it, okay? And this one is already in an equation form or in a formula, so we can just drag it down like that. So now we just keep going and going. Now we know there's a limit, okay? Because we know that when p equals to 64, that should be enough, right? So we know that we don't have to go too far, because as long as we hit, like 60 something like that, eventually we'll find the answer when it turns from true to false. So we just look at the boundary when it turns from true to false, and this is the answer. Okay, so when we look at this and go like, but that doesn't tell us what is the value of p. Well, I mean, that's easy to fix too. We just have, but this is not p, by the way. Okay, that's me doing confusing things. This is 2 to the power of p. And let me do that one more time. 2 to the power of p. All right, so now we have this column saying, what is the value of p? Obviously, this is 0. And then this is the previous row plus 1. Okay, so now we just have to drag this one down as far as we went. Or as if we get to the false, that's fine, okay, because we are not going to look any further than that. So now we focus on row 45, and we can see on row 45, p has a value of 42, and 2 to the power of p has a value of approximately 4.39 times 10 to the power of 12, okay? So I can just write down the answer of 42 at this point. So that's one way to do it. The other way to do this is to solve it by using math, okay? So let me get out of this, and I should quit. Turn that away, turn that off, and now we move on to this class. There we go. All right, so now I'm just going to solve it by equation, okay? So we know what we're dealing with here is we have x, which is given to you, and we want x times 2 to the power of p to be just less than or equal to, LE is less than or equal to, 2 to the power of 64, the whole thing minus 1, okay? So this is the equation that we are given with. So if you want to solve for x, okay, and the best way to do it is to look at it as an equation instead of an inequality. So just kind of look at this less than or equal to and treat it as if it is an equal to. Then you can solve for p, but that p is going to be an irrational number, which is okay. Okay, we'll get to the irrational number first. So now we get x times 2 to the power of p equals 2. Okay, so this time we just say that it's equaling to 2 to the power of 64, the whole thing minus 1. Okay, so now we have an equation. So given the equation like this, given that x is already a known value, you can plug this into Mathematica. Okay, you can plug it into Wolfram Alpha, which is a mobile app, and it will solve it for you. Okay, so that p is going to be an irrational number, but because we want x times 2 to the power of the integer version of p to be less than or equal to, so we just have to take the floor of that. Okay, so that means if I want to look at the math equation, then we have left floor of x equals 2, sorry, p equals 2, the floor of let's see, it's going to be the floor of the log 2 of, let's see here, okay, so it would be it's going to be a fraction, And then the numerator of the fraction is going to be 2 to the power of 64 minus 1. And then the denominator is going to be, I forgot about a plus 5. Not that it's really that important, but it's good to keep everything the same as presented in the question. So I have a plus 5 over here. So that means I have to do a subtract 5. So that turns this 5 into minus 6. And then the denominator is going to be simply x down here. Okay. So we check the matching of the parentheses. We close that one. And then we close the floor. So we have a right floor over here. And now everything looks good. It's not exactly rounding. It is, we are taking the floor, which means if the irrational p is, let's say, 2.9, okay, we'll still want to use 2 instead of 3. So because we are taking the floor and not rounding. Oh, the plus 5, yes. The plus 5 is for rounding purposes. That is true. Okay, let me wait for Quan to finish his typing. And then he or she, I cannot tell, but maybe there is no question. Okay, all right. All right, so this is the closed form, okay? And let me see if log can look better if I use \log. Yep, that looks better. Because log should not be italic because it is a math function. That's why it should be non-italic. Okay, so do we have any questions about how to solve for p using a formula instead of using a spreadsheet, which is a trial and error type of approach? The spreadsheet approach is not wrong. Okay, I want to re-emphasize to people who use the spreadsheet approach, it is not wrong at all. If anything, okay, it is a way of looking at this and go like, okay, how do we do this using a program? Because remember, your program, which I'll talk about today, is not supposed to use any double function. So you cannot use power, you cannot use log, you cannot use okay, power and log are the only ones that are really kind of useful, but you can't use those. So since you cannot use power and log, the spreadsheet approach is a much more iterative approach, and that's kind of what I want you guys to do for the next homework assignment. So shall we move on? Do we have any additional questions about number 1? Okay, it doesn't look like we got any more questions. All right, so let's move on. Next, click next. All right, so this one is, well, this one is supposed to be super easy. So you just plug in x into here, and then you plug in x into here, and find what is the answer. So now, if we round 15.55 divided by 10, now 15.55 divided by 10 is 1.555, right? So the round of that is going to be a 2. On the other hand, 15.55 divided by 10, and you take the floor of that, it's going to be a 1. So 2 minus 1 is a 1. And that's question number 2. But question number 2 says a whole bunch of other things, because it wants to explain to you that, to do this x plus 5 divided by 10 and the floor of that, that is just integer division. So we add 5, which is an integer operation, and then we take the sum of that and then divide that sum by 10, which is also an integer operation. So we do not need to use round, which is a double function. All right, so moving on to question number 3. So question number 3 is asking, let x equals to 4.774 times 10 to the power of negative 5. Express this value in units of 2 to the power of negative 21. Okay, so to solve for this, you just have to divide, because all we're going to do is to divide x by 2 to the power of negative 21. And then, but the answer also says round your answer. Okay, so this time you do have to do the rounding. Okay, don't just give me the integer part. Okay, you have to do the actual rounding. So let's see if we can use a spreadsheet to do that. Okay. All right, so I'm going to put it on a new sheet here. So if I use a spreadsheet to do this, I would just enter round of 4.774 e negative 5. You can see that spreadsheets also use exactly the same scientific notation, and we're going to divide it by power 2, 2, and then we have negative 21, I think. Yep. So negative 21 is the power of 2, close paren, press the enter key, and the answer turns out to be 100 over here. All right, so I'm looking at the text area of today's class, and I don't see any questions. All right, so let's move on. Click next. All right, so here's the really kind of interesting question number 4. So question 4 is asking you to solve for p again, and I want p to be an integer. Okay, that's part of the question. And this time v equals to 4.044 times 10 to the power of 28. But there's an extra constraint. Okay, so unlike last time, but where there's only one constraint, I just want the left-hand side to be as close as the right-hand side, but not greater than. This time I have 2 constraints, because I want x to be greater than or equal to 2 to the power of 52, but I also want it to be less than 2 to the power of 53. So how do we solve for this? Well, once again, there are many ways to solve for this problem. Okay, so let me just go ahead and use the spreadsheet method again. Yeah, I cannot overemphasize that I can abuse a spreadsheet to do just about anything, as most of you will find out in about a week or two. I use a spreadsheet to implement an assembler, which is kind of a weaker version of a compiler, but it's doable. All right, so let's go ahead and enter what is v. So v is, in this particular example, 4.044 times 10 to the power of 28. Okay, and now we just say, okay, let's look at all the possible p. And this time I'm going to do it the proper way. We start with 0 over here, and now we look at 2 to the power of p. So that's just the power of 2 to the is 2 to the power of a3 in this case. And now we want to compare. So the comparison, I think I can just use the lower bound and the upper bound up here, because there's no need to recompute these values over and over again. So we'll say the lower bound LB is, let's move this over here. So LB is 2 to the power of 52, and upper bound UB is 2 to the power, okay, equals 2 power to 53. Okay, there we go. And you can see that the lower bound is about 1/2 of the upper bound, which is to be expected, because one is 2 to the power 52, and the other one is 2 to the power 53 minus 1. Okay, I forgot the minus 1 is actually not going to be important. In fact, we cannot really tell whether there's a minus 1 or not. But now we want to see if we want to see if x, okay, so now we have to solve for x. Oh, okay, we have to move things around a little bit. Cut, paste, there we go. So now we want to compute x. Let's see. So knowing what is 2 to the power of 2, we can just go ahead and solve for x, because we know what p is. So we will go ahead and solve for that. So this x is going to be v, which is this value over here, divided by 2 to the power of p, which is this value over here. But once again, we have to use a $sign over here because I don't want the pasted version of this formula to change the row reference. So we have to lock the row reference by using a $sign. And then we can now check whether the constraint is satisfied or not. Okay, so we say constraint. So the constraint is in a conjunction, because I can't enter some an inequality like this, okay, to check for upper bound and lower bound. So we're going to use a conjunction where the first part is just checking whether it is at least as big as the lower bound. So we say, we refer to the lower bound, and then we say less than or equal to x, which is this particular cell. And then the other one is going to check it against the upper bound. So we want this value to be less than the upper bound, which is here, and close paren. And once again, every time we refer to lower bound and upper bound, they are not quote unquote floating with the referencing formula cell. So I have to lock the row number. So we have to insert a $sign when we refer to those two. So C2 and D2 now have a $sign in front of the row number reference. C4 is fine because we do want that part to shift as we copy and paste the formula. So it is false, okay? So that means we are not meeting the constraint requirement. So now we move on to the next one. P is going to be 1 plus whatever is before this row. And then the rest are just going to be copied down here, okay? And you can see when p increases by 1, x, the x that I have just solved is going to be halved, okay? But that's really to be expected, right? So now we copy and paste this, and once again, we know that if we copy and paste the rows up to like 64 times, we'll find the answer, okay? So we'll go to row 70 this time, okay? Ish, right? I mean, I don't need exact values. Uh-oh, yep. And you can see that there's only one row, which is this one here, that has that meets the constraint. That would be the answer. So we just say, oh, okay, we got it, 43. And some of you look at this approach and go like, well, that really is not a very mathematical way to get to the answer, right? I mean, I'm basically doing trial and error here. But the nice thing about this approach is it does show you by changing p how I'm affecting x. And I'm just basically saying, okay, if I keep changing p, I'm affecting x. I want x to be within these, greater than or equal to the lower bound, but less than the upper bound. So you can basically see how the trial and error approach really shows, how we can get to the answer. But some of you are not satisfied with this approach because you know math. And you say, but how do we solve this using math? Well, once again, if you want to solve this using math, what you can do is to change the inequality into a equality. So you can say, okay, let's just say that x does equal to 2 to the power of 52. That will enable you to solve for a p. Yep, exactly. So Aiden has got the right math. But once you solve for that p, then you have to decide what to do with the irrational version of this p here. Because if you say x equals to the lower bound, that p is going to be the upper limit. Okay, the irrational p is the upper limit of the actual integer p. So in that case, you have to use the floor operation to find the actual value. On the other hand, if you say x equals to the upper bound, 2 to the power of 53, and you solve for that p is going to be the lower bound, which means you have to use the ceiling function to find the actual integer p. Or you can go find the boundaries, okay? So you solve for p when x equals to 2 to the power of 52, And then you solve for p again when x equals to 2 to the power 53. So now you got two irrational numbers. But trust me, if there's only one integer between the two irrational values, that would be the answer, which should turn out to be 43 in this case. All right, so do we have any further questions? Because the next four questions they have different values, but in terms of the type of the question, they are basically just a repetition of the first four questions. So if there are no questions about these, I'll just go ahead and submit and make sure that I get points for these four questions. Are we good? Looks like it. All right, so I'm just going to submit, knowing that I did not answer four of the questions. And let's check the answer. Yep, so I got 1 out of 1, 1 out of 1, 1 out of 1, and 1 out of 1. Okay, that's good enough for me. Because I'm not sure how many of you took the personality test. To an INTP, what is important is I have proved that I understand what to do and the math behind it. I don't need to do it again to get all the points. The points are not nearly as important as me knowing how to get it done. Well, 50% is C in this class. I mean, that enables you to graduate. You may not be able to get to the CSU or the UC that you would like to get into. Yep. Well, I mean, 10 years from now, you guys will look back and go like, why did I bust my butt, ass and actually, spend that much time studying? Because your first employer may want to know about your grade, but when you switch jobs a few times, nobody cares about your transcript anymore. And I know people who started ARC, got hired as an intern for a company, and so far he has not returned to ARC to continue his education because he already has a really nice job. So, that happens too. Cool. All right, so now we're moving on to today's lab. So today's lab is a little bit special, so I'm going to use the rest of the time to at least describe how to set it up, okay? Because the setting up part is actually important. So the first thing is you're going to need a C compiler and a debugger. In previous years, I let people use or encourage people to use code blocks. Okay, so let me just go to the current the quiz that is assigned today. There's no passcode to this lab, by the way, so don't worry about the passcode part of it. I will talk about today's role-taking word, and it's going to be obvious once we get into this. All right, so we'll take a preview again. So this one is one of the C programming projects that you have to do for this class. And if you click on this link here, okay, it will download a zip file, and the zip file contains a project that is half baked. Okay, and then you have to use code blocks to finish the project. So that's fun. That's fine. That's one way to do it. If you already have code blocks installed on your computer and you know how to use code blocks, and that doesn't bother you, do it this way, okay? Because you already know the tool, you have it installed already. There's no need to go anywhere else to get things done. On the other hand, if you say, but I don't have code blocks installed, okay? And last time I took CISP310, the professor used VS Code or something like that. I don't have it installed anymore, or I just don't want to deal with having to install something because I'm using a Chromebook for this class. Okay, well, there's a way to do it too. So let me switch to this tab over here. All right, so this is, if you look at the URL, it is www.onlinegdb.com. This is really cool. You guys can go there right now. It doesn't need to sign in at all. If you want to sign in, it's nice because you can actually save your file. Okay, but if you just say I just want to test it, I don't need to save any file. You can just go there. Okay, it will let you in and play with GDB in C or C++ without anything, without signing in or knowing your identity. So this is a really kind of cool resource because it allows you to write programs in C or C++ without having to install anything on your computer other than a browser. Now, if you don't have a browser, I think we're in big trouble, right? So you already have a browser, and that's all you need in order to write your program. If you do sign in, then it will actually save your file for free. Yes, okay, it is different from Replit because this one has GDB enabled. The other one, I believe, does not. Is that true? Does anyone want to comment on whether Replit has GDB enabled for unpaid accounts? All right. Yeah, this one is not paid. I didn't pay a single dime, and it saves my my project. All right, but just knowing that this is a fairly easy interface to use doesn't mean that you're ready to start the project. Okay, so let me just kind of quickly describe this file, which I will download and put it onto today's text channel. So it'll give you a warning, but it's okay. It doesn't actually hurt anything. So I'm going to save this and overwrite the one that I have already in here. And then I go to the text channel and upload it over here. So we'll upload main.c. And now we have it in the text channel. Okay, so if you want to use code blocks, you don't need this file because this is a monolithic type of program. The one limitation of using online GDB is it doesn't allow the use of your own #include file. You can #include other files, not a problem. Okay, but if you make your own #include file, it doesn't handle that. So your entire project has to be self-contained in a single file. At least that was the case last time I used online GDB. Now, if it has enhancements, since then, and now it can handle a folder which contains your own header file, okay, that's nice, but I don't need it, okay, because this file, the file that I have just uploaded, main.c, is a self-contained file. Okay, it contains everything. You don't need to #include anything. So the first thing to notice is I have defined a structure, which is basically the same thing as a class in C++. So a struct is kind of like a class where all the members are by default public. So this one has got the sign, it has got the mantissa, which is a 64-bit unsigned integer. It has got the exponent of 10, which is 16-bit signed. And it's got an exponent of 2, exp2, and I don't know why it is highlighted in red. Probably because it resembles one of the functions in C. But this is exp2, it's really just the name of a member, and that is also an unsigned 16-bit integer. So number is a structure that's already defined like this. Parse state is not something that you have to be concerned about, simply because it is used for parsing. Remember the regular expression thing? Yeah, so that's what I need in order to parse the input string. And I'll show you how to specify the input string. Okay, so just hold on a second until I get to that part. And your job is to fill in the content of exp10 to exp2. Okay, basically we start with a non-zero exponent of 10, and we'll do whatever change we need with the mantissa and the exponent of 2 in order to get rid of the exponent of 10, or turning the exponent of 10 to 0. Okay, and the input, the parameter to this particular function is pn, which is a pointer to a struct number. Okay, so if you If you are not quite sure how to use pointers, okay, you might want to brush up a little bit, because in CISP360, they are supposed to have taught how to use pointers and also how to use structures. So that's kind of something that you might need to do. The rest, starting with parse sign, parse blah blah blah, parse parse parse, those are things that I did in order to convert the base 10 string, the base 10 scientific notation string, into the structure that you just saw. Okay, so you don't have to mess around with these functions. Okay, in fact, don't mess with these functions. Okay, because if you mess up these functions, then it's not going to parse correctly. So the main program starts here, and I do make use of the argument that you pass to the main function in a C program. And this is how you specify the string that you want to convert. Okay, and I'll illustrate how to do it, at least in online GDB. If you want to do that in code blocks, the instruction is already included in the lab. So if you want to do it in online GDB, just kind of watch how I do it. And since everything is being recorded or streamed to YouTube, you can always kind of pause and watch it again if you don't catch everything. The first part, which is the kind of awkward looking code with a while loop, this is the part where the program parses the arguments that is passed to the command line program, and I'll illustrate how to do that. Okay, but you don't have to modify this at all. I'm just illustrating the structure of the program. So after we parse the string, which is a base 10 scientific notation, and capture all the data into n, which is a struct number, then we pass the address of n to the function that you're supposed to work on. So everything that you need to do is in exp10 to exp2. And I have put a breakpoint here already. So to toggle a breakpoint on the line, you just have to click to the left-hand side of the line number. Okay, so it's really easy. It is the same way that you set up breakpoints in code blocks or VS Code. Most IDEs now, use this, convention to set up breakpoint. So now we are ready to debug the program. So this is the part where you might want to write down the time mark. It is 7:37 right now. So you might want to write it down because you might need to refer to this step again when you're actually doing your lab. So what we do is we click debug. Okay, so do not click run. Okay, clicking run is not going to work. So you want to click debug. So when you click debug, it's going to go through the compiling process, and I made a problem here. Okay, so that means I have to re-upload the file. I made some last-minute change, and I forgot to recompile and check it. All right, so line 154 is right here, and I have been writing too much code in JavaScript. All right, so I'm gonna re-upload the file. Does everybody know, or at least some of you know what I was referring to when I said, I must have written too much code in JavaScript? Okay, Aiden knows. All right, so I'm going to re-upload the file, and I'll delete the other one so we're not causing confusion. Okay, source file to use in online GDB. There we go. And we'll get rid of this one. Delete message. There we go. All right. And then we'll pin the other one, the new one. There we go. All right. 119 unary minus applied to unsigned type result still unsigned. Oh yeah, I forgot about that one. Okay, let's debug again. Nope, no problem. So Aiden must be using a. Okay. All right, so it does work now. Okay, so now we are in GDB. Oh, okay. Yeah, Visual Studio for some reason is very picky about sign stuff. So anyway, if you're using Visual Studio, you need to cast something, to get rid of the problem that Aiden just mentioned. But assuming that you're using code blocks or online GDB, you don't have to do that. The program does compile. But the important part is once you get to GDB, okay, if you see GDB, the prompt, and then the blinky cursor, then you type run, okay, R is enough. You can spell out the entire word or you can just use R. But this is the important part. You have to specify a -n, which is known as a switch in a command line program, usually in Unix or Linux type of environment is known as a switch. But what this is really saying is the following is a base 10 scientific notation to be converted, okay? So I'm going to now specify 3.14 times 10 to the power of 0, okay? Which is really just pi, okay? And then when you press the enter key, the program will start to run, okay? So when you are testing your program, you have to remember when you run the program, you have to specify what is the string that you want the program to convert into a quote-unquote double, okay? So when I press the enter key, the program runs, and now we get to the breakpoint. Now, obviously, this program is not doing a single thing, right? Because there's nothing between the braces. But what you can do at this point is to say, I want to know what is Pn, okay? Now, trust me, that is not going to be very productive because Pn is just a pointer. All it's going to tell you is, hey, Pn is pointing to this location in memory, and it is supposed to be of type struct number. Great, not helpful. Well, this will be more helpful because this is not asking GDB to print where it is pointing to, but what is the content that is being pointed to by Pn. Now that is a whole lot more helpful because it tells you that the sign bit is a 0. It tells you that mantissa is 314. That is not a typo. It is not an error, okay? Because on last Tuesday, we already talked about this, okay? We only want to use integer arithmetics for the entire program that you're writing here. So if anyone is using power, if anyone is using log, that will get automatic deduction, okay? Because we are not supposed to be using anything in double, okay? Or float. So to compensate for the mantissa, which was 3.14, now it is 314. This is how we compensate for that. The exponent of 10, instead of a 0, now it is a -2. So if you think about it, okay, 314 times 10 to the power of -2, hey, that's the same thing as just 3.14. That is how we can represent everything just using integers, okay? EXP2 is by default a 0 because that's the whole purpose, right? We want to tweak the mantissa and EXP2 to get rid of EXP10. That is the whole purpose of this entire program. All right. So this is how we set it up. This is how we run it, okay? Now we go back to the notes. We got about at least half an hour. And I think, since we already talked about some of the notes last Tuesday, I think we got enough time to finish the discussion of the material that you need to get this done. So now we're back to Canvas, and let's go back to the class notes. So the homework assignment is called negative exponent because it's assuming the exponent of 10 is negative to begin with. I just clicked on the wrong link, by the way. And we'll click on this one. There we go. All right, so the description of what you need to do is already in here. So your code should take the struct number pointed to by parameter Pn and preserve the value. Okay, so you want to preserve what value is being represented, but you also want to satisfy these requirements. The mantissa should end up as a value that has bit 63 set. In other words, if you count all the bits starting from 0, okay, I want bit 63 of an unsigned 64-bit integer to be a 1. That is what this sentence is saying. EXP10 should be a 0 after the algorithm is done. Okay, well, that part is not surprising because we just want to get rid of the exponent of 10. EXP2 can be any integer. Okay, well, you have negative 32,000 something to positive 32,000 something, and I guarantee you that is enough. Okay, you have enough range with a 16-bit signed integer for EXP2. The represented value v should be preserved as much as possible. Now, I have to say as much as possible because it is not going to be exact, okay? But we want it to be as much as possible. To run the program, so this part is only applicable when you are using, well, okay, most of it is only applicable if you're using code blocks. Parts of it is also applicable if you're using online GDB. When you're done, okay, this instruction is only applicable if you're using code blocks, is to zip up the entire folder and then upload it. On the other hand, if you are using online GDB, then you can just go ahead and upload the .c file that contains your solution. Okay, so do we have any questions about, what to do, what to turn in, and what the program is supposed to do? Okay, we don't have any questions here. All right. Okay, so given that there are no questions here, we will go back to the whiteboard, quote unquote whiteboard, and then we'll use an example to illustrate what your program will need to do. So let me just say that in this particular example, v equals to negative 4.56 times 10 to the power of, since it has to start with a negative value, let's make it negative, let's see. I just have to make sure that it's negative, 100 is fine. So negative 100, that may be too much. Let's make it negative 25. There we go. So this is the v that we are dealing with. And the e here, I have to, okay, let me not use this. I'll make it very clear, okay, because we want to times 10 to the power of negative 25, okay? This is what we want to do. So the program is already going to do parts of it for you. So, when you look at what PN is pointing to, that is going to be a structure. But in that structure, you will see that Mantissa is already 456. The sign is not that important, so you can pretty much ignore the sign. Mantissa is going to be 456, and then EXP10 is going to be whatever we see here, which is negative 25 minus 2, because we have to shift the decimal point 2 places to the right-hand side. And for each place that we shift the point to the right, we have to decrease the exponent of 10 by 1. So this time we have to decrease it twice. So that will make it negative 27. And it will also automatically give you an EXP2 to be 0. That's just initialized to be 0. So that would be the beginning condition of this particular example. So what do we need to do? Well, how do you increase the power of 10 from negative 25 to negative 24? What can you do to the Mantissa that will allow you to increase the power of 10 by 1? Come on, guys. You guys know the answer because we talked about this last Tuesday. Yes, division by 10. Okay, very good. So in terms of math, okay, it's pretty easy, okay, because we are just saying that, okay, if v equals to, so I would first state the expression. We have m times 10 to the power of, I'm just going to use E10 here. It's the exponent of 10, it's EXP10 basically, but I am just using E in this case, times again 2 to the power of E2, which is the power of 2. Okay, so that is V. Okay, V is always, okay, represented by a mantissa of some kind. The mantissa in this case is just going to be something that fits within a 64-bit unsigned integer. E10 is an integer. E2 is also an integer. So E10 begins with a value of -27. E2 begins with a value of 0. And then M starts with a value of 456. Okay. So now we go look at this and go like, I can do something like this. Okay. I can divide M by 10. Okay. So we'll have fraction 10, M, and then a 10, like so. But I can adjust E10 or the exponent of 10 and increase it by 1, right? So I can take this and say just add 1 to it, and now I am preserving the value of V. Okay, because the division by 10 is canceled out by the exponent of 10 being 1 more than what it used to be. And that's how we can gradually get rid of, okay, not get rid of, but to turn the exponent of 10 to a 0. But we look at M divided by 10, and M is 456 to begin with. And this division, remember, you cannot use double or floating point calculations. You cannot cast something to a double or a float, then do the division. You have to use integer division only. So the integer division is going to introduce quite a bit of error when you divide 456 by 10, because the 0.6 is gone, okay? And that is, that's just losing a lot of precision. So if you keep dividing the mantissa by 10 and you say, oh, we just have to do it 27 times, what happens when you divide 456 by 10 27 times? What do you get? Well, you don't need 27 times, you just need like, what, 3 times? What do we end up with when we divide 456 by 10 as integer division and we do it 27 times? What do we end up with? 0, yes, okay. Well, yes, it is a single 0 and also a whole lot of zeros because it's a single value of 0, but it is represented by 64 bits of zeros. So it's both 1 0 and a whole lot of zeros. But the idea is it is 0. We have lost, okay, because the value being represented is M times something. So when M is 0, there's nothing left, okay? Okay, so that may not be the best approach to do, right? So what we want to do is now to say, I think we need to make the numerator or the dividend to be as large as possible, okay? So now, okay, so I'll just do it step by step, okay? So instead of just doing this, we say, I think if I multiply M by 2 and then take care of the extra multiplication by 2 by decreasing the power of 2 by 1, that would still preserve V, okay? So when you look at this, this multiplication by 2, which is this part here, is canceled out by this subtraction of 1 of the power of 2. Okay, so they just kind of cancel out. So now instead of using 456 and divided by 10, I'm now using what, 902 and divided by 10. So 2 out of 10, excuse me, 2 out of 900 something, which is the precision that I'm losing, is better than 6 out of 456, because so that's good, right? But it's not good enough. So we say, I think we can do better, because if I make this 4 and adjust this by 2, then I'm now looking at a larger numerator and basically a bigger dividend. And when I divide that dividend by 10, yes, I'm still going to lose the remainder, okay? but it's not going to be as much, okay? In terms of a percent loss, in terms of precision, I'm not losing as much. But I think we can do better, right? Because, it's only 456. I think we can multiply by 2 a whole bunch of times before we run out of digits in the 64-bit number, right? So you basically just have to say, okay, let's try 3. We are not quite blowing up the 64-bit number yet. Let's try 4. We are not quite blowing up the number yet. So you keep doing this, okay? So I'm just gonna say ... right? Until what? Until you find that power of 2, that will push m times 2 to the power of, let's call that p, because we use p a lot in the homework assignment that was due today. So until you get to that point, we can keep doing this, right? But you're not really keeping track of the p, or the power to 2, because what you can do is you keep multiplying m by 2 in the loop, but you have to know when to stop, okay? So that is where the notes come in and go like, okay, you keep doing this until this condition is true. So let me do this here, okay? So I'm just replacing the 4, with p, and the idea is to find out when to stop. All right? So are we kind of making an association of what we need to do with this program with the lab that was due today earlier? Because I certainly hope that there's a connection between the two, right? So once we get to this point and we are ready to do the division, we go like, but this division is not technically a straightforward division because, strictly speaking, because text says no floating point number division. So the division is actually an integer division. In other words, in terms of math, if you want to express this to your math professor, this is what we're doing. Okay? In terms of math, this is what we are doing, but in terms of the operation, it's not what we are doing because we are dealing with an integer division. So when you perform an integer division, it's the same thing as taking the floor of the actual division. Okay. But Tech, you mentioned something about a bias last Tuesday. A bias is basically having all the errors erring in one direction. Because when you take the floor of a particular value, in this case, this is a rational number, okay? But it is not an integer, okay? So when you take the floor of a value that is not an integer, you always, the result is always less than what it is supposed to be. We are okay with the error, okay? Because by making m times 2 to the power of p to be as close as we can get to 2 to the power of 64 minus 1, we have already minimized the error. So minimizing the error is not the issue here. The issue is when you take the floor function, we're always erring in one direction. The resulting value is always less than what it is supposed to be, which is problematic because we're doing this in a loop, right? And every time we do this, we're introducing an error, but only on one direction. So that means after performing this a few times, we end up with a larger error because it's all going to be cumulative on one direction, in one direction. So we need to do rounding. But to do rounding, which is the same as adding 0.5 to it, okay, so I'm just gonna, since I'm so fond of copying and pasting, right? So we'll just go ahead and say, hey, rounding is easy because we just have to say, just add 0.5 to this thing before you do the floor. Then it's the same thing as rounding. There's no need to do the actual round function, which is a double function, right? But then you go like, but text also said, adding 0.5 is not allowed. Okay, what are we gonna do? Well, you can always change the 0.5 and change the representation of the 0.5 to 5 divided by 10, right? That's 0.52. But tech, that's not going to solve the problem, because if you do an integer division of 5 divided by 10, that's just going to give you 0. It's not going to do a single thing. Well, that's why we need to do the math. That's why the humans need to do the math before the computer gets a chance to can get a chance to work on it. Okay, so what we'll do is we're going to say, hey, since the denominator is the same, with all the components of the addition, so we can just say, yeah, we'll move the plus 5 over here and get rid of the 5 divided by 10, which is outside, right? Oh, let me think about this. M times 2 to the power of p is just after, we basically multiply, we just keep adding m to m a whole bunch of times until it is right about to burst, okay, right about to run out of digits in the 64-bit number. And then we add 5 to that thing, which is still an integer arithmetic. And then we divide it by 10. But since we're taking the floor of the division by 10, that is also an integer division. So now, when you look at this entire thing, they only involve integer arithmetic, which is cool, okay? Because, there are a lot of processors out there without the support of a floating point unit. So if you try to say, oh, we're going to import the double library, okay, the math library to do double, well, it's easy for you to do, because all you have to do is to pound include math.h, or to use a switch on the compiler and just say that we're going to link with the math library. But when that program runs, okay, it's going to chew up a lot of processing resources, and you may end up losing so much resources that you can't really get whatever you want to be done with that processor. I mean, trust me, I have encountered situations like that, okay, where I use a very wimpy 8-bit processor, and I can't even do squares, okay? If I do any squares or multiplication, I would run out of processing resources. So I have to translate everything to addition, comparison, and subtractions. So sometimes you have to do these tricks just because you don't have the processing power to have the convenience, to afford the convenience of using high-level math functions, okay? So if the highlighted portion can all be done using integer arithmetic operations, what about these things? What about adding 1 to the exponent of 10? Oh, that's easy to do. What about this thing over here? Well, guess what? Every time you multiply m by 2 or doubling m, you just have to decrease e2 by 1. Easy as that, okay? So is everybody seeing what to do, with this particular program? I hope you guys are getting an idea of how to do this, because what is happening is m in the end is going to be updated. Okay, I use left arrow for an assignment operation, because all of these single equals, they really basically are equality. This is an assignment operation. We are updating m by this expression here. Okay, so I'm gonna do the lazy thing and just copy and paste a bunch of stuff. And you cannot see because I'm doing this off screen. Control Shift C, Control Shift V. There we go. All right. This is how we want to update m after we figure out that p, or this is the effect of updating m after we figure out what p is appropriate for this operation. Then we also want to update E10, right? So E10 is easy because it is just updated to what it was, E10, and we can say, we can bump it up by 1 now. That's how we update E10, the exponent of 10. And then this is how we update E2. So E2 is updated by a subtraction operation, and we are subtracting p from E2. So these 3 steps is what to do after we figure out what P is supposed to be. Now, you don't have to do all this at the end of figuring out what P we should use. Instead, you can basically just use P as 1 and then update M, update E2, accordingly. But don't do the division by 10, right? In other words, you just want to make M larger and larger and then make E2 smaller and smaller until you can't do that anymore, until M is a really big number, is using all 64 bits of the integer. Then you go ahead and divide it by 10 and increase E10 by 1. And then you check whether E10 is still negative. If so, go for another iteration. That is the general strategy of this homework assignment. So now the question is, well, you talk about this, but can we find somewhere that actually gives us a clue of how to do this homework assignment? Well, the answer is yes. We have been talking about that since, not since, but we talked about it on last Tuesday. So we'll go back to the notes and I'll point out to you where you need to read. So we go to floating point number representation, this particular module. And you want to go to, I think, 5.2.1. Yep, there we go. This is going to give you a clue of what to do. And I intentionally did not give you the condition of the loop. Okay, so every time I say as long as, it's kind of suggesting that we have a loop here, right? And it does say something about, if as long as M is less than or equal to the largest numerator value minus 5 divided by 2. The minus 5 is necessary because the first thing we are going to do is to add 5 to M. So we want to, actually it should be the largest numerator value divided by 2 minus 5 because we're adding the 5 first. So we have to kind of change the way we express that. Yep, okay, so let me change the notes here. Okay. Not that most numbers would actually break because of that, but I think it is good for me to fix the notes when it is wrong. And this module is 0296. Modules 0296. So you might want to think about questions to ask at this point because this assignment is due in a week. I do believe you have enough information to begin with. The information is all here. The question is, are we linking all the concepts together? That really is the question. And I'm already at the point. So as long as M is less than or equal to the largest numerator divided by 2 minus 5. Okay, so just have to change that order. Divided by 2 minus 5. Okay. And let me republish this. All right, so let me update the web page. And now it is correct because now it says as long as M is less than or equal to the largest numerator value divided by 2 minus 5. Okay. So now we got a few new questions. Okay, what is the largest numerator value? It's whatever the maximum is with a 64-bit number. Okay, so the question is, what is that number? What is that value? You got a few ways to specify that value. You can put it into a calculator and then copy the 19-digit number over. That will work, but not really fun, right? Actually, let me tell you this, it's not going to work. If you do this on a calculator, most calculators will not give you 19 digits of significant. It would not give you 19 significant digits, which means what you will end up with is really just an approximation of the largest numerator value. And chances are your calculator would also give you that number in scientific notation too. So that means you have to figure out how many zeros to pad on the right hand side, ending up with a value that is actually not exactly the same as what we need to use here. So I'm going to tell you guys what to do with this portion. Okay, how do we get to the largest numerator value? So the way to do that is to make use of, there are different ways to do it. But the best way to do it is to understand what is in stdint.h. Okay, close, Daniel, close. All right, so you can look it up online. Okay, don't look up stdint.h because it's not a valid domain name. .h is not a valid one. Okay, but in here, it describes a whole bunch of stuff. Okay, since we're looking for maximum value, I'm just so lazy, right? There we go. So it has these, okay, and it has, let's see, there we go. Maximum value of exact width unsigned integer types, uint n underscore max. Okay, if anyone is just going to type in this in the program, as in uint n underscore max, I will not help you. Because, okay, I know it sounds really mean, and sometimes I am mean, but in this case, it's because if you see that n is italic, it is basically telling you that it's just a placeholder. So this n is a placeholder for the actual width of the type that you're dealing with. And I am not going to tell you what n is supposed to be in this program. Okay, so I want you guys to figure it out. So Aiden says, can't we just do typecast -1 to unsigned 64-bit underscore t? The answer is yes, you can do that as well. But that is a very obscure way to specify a largest positive value. Tom says, do we put the type there or do we put the amount of space for n? I will let you figure it out. Okay, because you're proposing two ways to do it, right? So you can try one way. If it doesn't work, try the other way. I can tell you that one of the two ways is correct. Yep, cool. The reason why I want you guys to go figure it out is because if I give you the solution, you will get the homework done faster, but you're not going to remember that as well. Okay, because if you figure out something yourself, you are not just memorizing the piece of information, which is the objective for this particular piece of this particular homework assignment, but in the process of figuring that answer, you are making multiple pathways to that piece of knowledge. Okay, and those multiple pathways is going to be helpful in the future. Okay, so when we are not talking about this homework assignment and we are talking about something that you have to do in your occupation, when you have a job, then being able to figure out things now will build additional pathways, neural pathways, so that you can link different concepts using multiple paths so that things are interconnected better. Okay, that's the better way to put it. And what that is going to help you is in the future, if a problem is requiring you to look into it and you have to solve the problem, you don't have a single pathway anymore between all the concepts, which means you can now solve a bigger problem that you have not seen before, because your mind now has multiple pathways between the concepts. If I give you the solution, then you have one single path, which is also known as a critical path to that concept. If you, for whatever reason, lose that path because you got other things to remember, you have to learn new programming languages and whatnot, so you start to lose a path. And if there's only one path linking back to the concept, then it's very easy to lose that path. When there are multiple paths to the same concept, then it's not nearly as easy to lose that concept. So that's why sometimes I would sound really mean, because I know the answer, but I'm not telling you. But instead, I tell you how to find the answer, because by going through that process, you will build the pathways that you will later on find useful. Now, if somebody says, but what about those people who change their career plan and decide not to study computer science or not to become a developer? Well, I can't really say anything about that, right? Because I am using the assumption that you guys are all moving forward to become a computer science or person or computer engineer or a developer. So that's kind of the long way of me explaining why sometimes I may sound mean by not answering a question directly. All right. So are there any other questions about this? Let's go back to the notes, okay? So we want to find out whether there are some additional stuff, okay, that is difficult to do. There's no actual floor operation, right? Because the whole thing of plus 5 divided by 10, they are all integer math, okay? So there's no actual floor operation in this case. And then there's also the structure of the loop, okay? I can tell you that there are multiple ways to structure the loops, but the way that makes more sense to me is to have a nested loop. Okay, you have a nested loop. The outer loop is basically just saying, hey, as long as exp10 is less than 0, let's do this. Okay, that's kind of what the outer loop is going to do. The inner loop has the responsibility of saying, I want to make m as large as possible. That's the job of the inner loop. So after the inner loop exits, m is already as large as it can get, then we can go ahead and do the division, update E10, go back to the beginning part of the outer loop to check again. If we need to go for another iteration of the outer loop, go for it. If not, we can exit the outer loop. All right, so that is as far as I want to describe it, so that you guys have a starting point. But let me switch back to the whiteboard. So the whiteboard, which is right here, is actually going to be helpful, okay? Because what your program or what your inner loop is doing is the ... okay? Because you're basically saying, okay, I can multiply m. There's room for m to double again. So the question, okay, so this is the other thing that I should probably mention. If you translate this, okay, m is less than or equal to the largest numerator value, which we have talked about, divided by 2 minus 5, actually that should work too. Okay, so never mind, okay, because at one point in time, I was not describing like this. I was describing it as if you double m again, it's going to overflow a 64-bit number. That was how it was described. That was, well, let's just say that, a lot of people did not understand how to convert that one to proper logic, to proper comparison. This one should work like right out of the box. Okay, so I think we are ready to get started with this program, unless someone has a specific question about this. I'm looking at the text channel right now, and if you got a question, go ahead and put it into the text channel or direct message me. Either way is fine. It can be a question related to how to use online GDB. So the URL of online GDB is literally onlinegdb.com. Oh, that reminds me. The word to take row today is GDB, all lowercase. I'm going to type it here. Okay, word for row taking is GDB. There we go. And the lab itself has no passcode. You should be able to get in right away. So do we have any questions? Because I want to make sure that you guys get all the information to get started with this project. Okay. All right. So what I will do is I can upload the markdown file or the HTML corresponding to this markdown file. Either way is fine. I wonder what is the best way to do it. I think we can do this. I can just print it as a PDF and then post the PDF. Super easy, right? There we go. And I'm now going to Discord to upload that. And this one is going to be, oh, how is it going to be labeled? Okay, so that's not going to work. Okay, once I get here and look at modified. That has to be the file. Okay, so I'm going to upload it here. All right, so I just uploaded a PDF. Hopefully it is the file that I was intending to upload. Why is the lab called negative exponent? Because we start with a negative exponent of 10. It's literal. It's really literal. We start with a negative exponent of 10 and we want it to be 0. That's why it's called negative exponent. All right, so I'm just going to download the file that I just uploaded and make sure that it is what you see in the whiteboard area. Can anyone verify that? Okay, let me try that again. Download gives me a PDF, but it doesn't show me the content. Okay, now it does. Okay, cool. Yep, it is exactly what we saw in my browser. So now you have the whiteboard. Basically, they're step-by-step explanations of what we are trying to do. So I hope that is helpful. Okay, thank you, Kara, for confirming that it works for you. And oh, no problem. I mean, that's pretty easy for me to do. Cool. All right, so this is one of the few days that I can end the class, not like, being 10 or 20 minutes late. So it's only like 2 minutes late today. So unless you guys have any questions, I am going to stop the recording, but I'll stay online, to answer questions. And I think it's a good idea to get started, okay? At least get started with the programming environment, okay? If you want to use code blocks, use code blocks. If you want to use online GDB, try it out, okay? Just give it a try, okay? Make sure that your program compiles, you can run the program, you can set breakpoints, and don't forget that when you run the program, you have to, okay, let me show you again. I know I'm kind of nagging at this point, but just make sure that when you run the program, use debug, okay? And when you start the program, you have to tell it what number you're converting. So you have to run with a -n, specify the value that the string that you want to convert to double. Okay, so you can say 44.56 times 10 to the power of -25. Okay, and then press the enter key, and just make sure you can at least get to the breakpoint. For those of you who know how to use revision control or get, okay, it's a great idea to use revision control because this program is not going to be long, okay? I can tell you that your part of this code should not exceed 20 lines at the most, okay? So it's not going to be a long program, but you still might want to do revision control just so that you can say, okay, this program is at least working up to this point, okay, that I'm expecting it to work. So that way you check it in, and then if you make any changes and the program doesn't work at all anymore, at least you can do a diff to find out exactly what you did to break the program, and then you can fix it pretty easily that way. All right, so I'm just gonna sign out, okay, instead of keep on babbling. But I will check the text channel and also the direct messages. Oh, Tom is typing something, so I'm gonna wait. Oh, okay, you too. Probably have a good dinner for most of you, and then try to get started with this project as early as possible. Okay, just so that we can get rid of the unknown factors as quickly as possible. All right, good night. I'll see you guys on Thursday.